University in Portugal, and his work focuses on the intersection of security proofs and verified implementations.
So, thank you very much for the introduction, and just to complement it, just say this is a joint work with Vitor Pereira, Manuel Barbosa, Gilles Bab, François Lucas, Benjamin Dubois, and Marcel Laporte. So this is the outline I intend to follow for today's presentation. I'll start by showing some motivation that led us to do this work. Then I'll explain the two components of our stack, which is first the certified generation of Boolean Circles from C programs, and then I'll once again securely evaluate those Boolean Circles. Then I'll present how these two components can work together, and I'll finish up with some conclusions. So I would like to start by showing an overview of what multi-party computation and secure function evaluation is. So multi-party computation is a kind of cryptographic technology that allows n parties holding n inputs to securely evaluate a function f. And by securely, I mean that no information about inputs can be disclosed. Of course, there is also a correctness property that says that honest parties does not output any incorrect result. One interesting feature of multi-party computation that it allows the elimination of the trusted third party. And secure function evaluation can be seen as a special instance of multi-party computation for two parties. One interesting feature of MPC is that it can be seen as a stack. So computation over encrypted data typically requires specifying a computation. And we know that there are secure protocols that can be applied for very simple tasks like multiplication, addition, or the evaluation of Boolean gates. And we also know that these simple tasks are composable. Therefore, one can describe complex computation as express them as sequence of these simple tasks. And the evaluation of this complex computation can be done by some kind of distributed virtual machine that knows how to execute low-level protocols in sequence or in parallel. I have here two examples of this kind of stacks. The first one is Threshold, which is a Java-based secure computation framework in which complex computations are described as Java structures. Then these Java structures are compiled into low-level gate streams, which can then be evaluated by gradually executing protocol for these low-level gates. Another interesting example of such stacks is the ShareMine platform, which is a secure computation application server. And in here, complex computations are described as security-aware C-like DSL named secrecy. Then secrecy code is compiled to DS bytecode, and ShareMine contemplates an engine that executes this bytecode by simply mapping each instruction in the language into a distributed protocol. So nowadays, MPC has achieved an interesting state of maturity, and there are actually some systems that are being provided to end users as more and more companies start to explore this kind of technologies. And these kind of technologies also come together with some interesting.
Could you make sure your microphone is turned on?
That was good.
It will be in a second. One more time, just try it.
It's good now?
Yes.
So these kind of technologies also come together with some interesting challenges, mainly regarding formal verification. So regarding formal verification, we know that there are some nice tools for program verification like CompCert or COC. There are also some nice tools for cryptographic reasoning like ExeCrypt or CertiCrypt. And during this work, we were curious of how can one combine these tools with this kind of MPC stack structure that we've seen before. And namely, we're trying to answer these two questions. Is the existing technology enough to reason about MPC and SFE? And are these technologies sufficient so that we can transpose theoretical guarantees into concrete software instantiations? Also, it comes together with some functionality and correctness challenges. And our work tries to precisely address these kind of challenges, as we present here the general architecture of our stack. So as you can see, a C program is first fed into CircGen, which is our certified compiler for Boolean circuits. We have two versions, one optimized and one fully verified and non-optimized. then having a Boolean circuit, we can securely evaluate it using our verified YAO evaluator, which executes a verified implementation of YAO SFE protocol. So let's see how can one generate Boolean circuits from C in a certified way. But first, let's analyze this abstraction gap between what the user wants and what the virtual machine knows how to evaluate. So typically a user wants a high-level, simple language close to C in which he can easily express complex computations. However, a virtual machine typically knows how to evaluate computation descriptions of this form, which is actually a Boolean circuit form. So the solution to this, to remove this abstraction gap, is actually to compile C to Boolean circuits. And one may ask, why Boolean circuits? Well, we know that there are multiple protocols that can securely evaluate Boolean circuits. Boolean circuits can be used to other cryptographic primitives like functional encryption or homomorphic encryption, and some useful steps of this compilation can actually be applied if we target other formats like arithmetic circuits. There are some interesting solutions that compile C to Boolean circuits. However, these are non-verified, and some errors were actually found in circuits that were widely used in crypto. So our goal here was to have a certified C to Boolean circuits compiler that was coupled with a semantics preservation proof. And to do so, we relied on CompCert compiler and on the COG proof assistant. This is the general architecture of CircGen. So as you can see, a C program is first fed into our front end, which are actually the first compilation steps of CompCert. And as soon as we reach the RTL intermediate representation, we change to our backend, which was fully developed from scratch in COG. We do some more transformations until we reach the final Boolean circuit representation. So in this presentation of CircGen, I will use this program as example, which is actually a representation of the millionaire's problem. So the first step, the front-end passes, as I said, are the first compilation steps of CompCert. And we use CompCert to do, of course, to parse the C program, to perform some certified loop enrolling, to inline functions, and to address some RTL optimizations like constant propagation, common subtraction elimination, and redundancy elimination. And this is the aspect of the program after the front-end pass. So as you can see, we only have one function now, since the millionaire's function was inlined into the main function, here represented in red. And you can see that we have here the memory instructions typical from RTL. So the first intermediate representation of our backend is RTL-C language, which stands for RTL circuits, which is mainly RTL with control flow enforced by conditional execution. And here, for every instruction, a path conditional formula is assigned, and actually the execution of the instruction is guarded by this path conditional formula. We also do two more additional transformations at this step. The first one is constant propagation, and then we transform the program into static single assignment format. Here is the aspect of the millionaire's function after this pass. So here on the left, you have an RTL-C program. As you can see, every instruction is guarded by a path conditional formula. And on the right, you have the same program in the static single assignment format. So moving on, the next intermediate language is called HL-Circ, standing for high-level circuits, which is a language that describes Boolean circuits with complex gates. And here, circuits are specified by a sequence of wire buses that are fed and collected from these complex gates. Topologically speaking, one can see that every line in a program in HL-Circ matches the wire bus of the gate authority, and then gate inputs are specified as connectors that collect wires that previously appear in the program. And this is the aspect of our program in the HL-Circ language. So for readability, we can see that the output line, the final line output just says that the output is the first 32 bits of line 20. And we can see that line 20 is an update gate that transposes the first 32 bits of line 19 into the first 32 bits of line 5. And one can continue moving on from bottom to top until reading this program like this. So having a high-level circuit, we now are interested in having a low-level circuit. And to produce these low-level circuits, we need to instantiate high-level gates. And to do so, we rely on concrete definitions for these gates, meaning that every gate will be mapped into the corresponding definition. We say that the verification of these individual gates is orthogonal to our work. And finally, we expand the entire circuit into Boolean gates. Some interesting observation at this step is that it is possible to optimize this process of gate expansion if we do something like memoization or removal or entries not contributing to the output. And actually, we can achieve better circuit performance if we perform these optimizations, knowing that the verification of these optimizations is still a work in progress. And this is the aspect of the program of our Boolean circuit that was certified generated from the C program that I showed you before. Here are some gate counts of circgen, and as you can see, for certain classes of Boolean circuits, even the fully verified and non-optimized version of circgen behaves well when comparing with CBMC GC. So now that we have certified generation of Boolean circuits, let's see how can one securely evaluate them. And to do so, our approach was to come up with a verified implementation of YAO secure function evaluation protocol. And to do so, we used the EasyCrypt proof assistance to formalize the protocol, to prove its security, and to extract correct by construction code. One interesting challenge in this work was actually to explore the verification overhead, both in terms of cost, in human resources, and in development time, and also in terms of efficiency of the end results. So I will just briefly explain the YAO SFE protocol. Bob, holding its input x2, starts by gargling the circuit. And by gargling the circuit, I mean that he creates a truth table for every gate. Then it replaces the input-output wires by cryptographic keys. And using these cryptographic keys, Bob is then able to encrypt all the truth tables. Having a garbled circuit sends it to Alice, and then they perform an oblivious transfer protocol so that Alice can learn the encoding of Bob's input. And during this oblivious transfer protocol, two security assets must hold. First one, Alice must only learn the encoding of Bob's input and nothing more. And of course, Bob cannot learn nothing about Alice's input. Then Alice, having Bob's encoding, the garbled circuit, can obliviously evaluate the circuit. Here's a modular proof of security for YAO SFE protocol in which we relied, what's done by Bellari et al. And as you can see here in this picture, the central rule was developed by a new primitive called garbling scheme. And the authors prove 4 very interesting results. The first one, that the construction of a garbling scheme can be obtained via a dual key cipher scheme. Then the construction of a dual key cipher scheme can be obtained via the dual masking construction and via a PRF security assumption. They also proved that for certain classes of garbling schemes, insecurity implies SIM security. And finally, they proved that a secure SFE protocol can be obtained if we combine a SIM secure garbling scheme and a secure oblivious transfer protocol. Here's our proof. As you can see, it's very similar to the original proof. However, it's with just a simple and slight modification here on the security model of the dual key cipher scheme that still allows one to do the dual masking instantiation. So here in this picture, I include the concrete definitions of the cryptographic primitives. So as you can see, an oblivious transfer protocol was obtained using an entropy smoothing hash function and relying on the decision diffie-Hellman assumption. A concrete definition of an insecure garbling scheme was used using a concrete definition of a dual key cipher scheme that was used using an abstract PRF. And then, using the result from Bellari, we proved that the garbling scheme was insecure, was actually also SIM secure. Then, combining these two concrete definitions of the primitives, we came up with an implementation of a secure function evaluation protocol. Here are some proof highlights and challenges that will help you understand better how the proof was carried on. So first, we did some compositional reasoning in an abstract setting. We proved the protocol secure under an abstract oblivious transfer protocol and abstract garbling scheme. Then we proved the garbling scheme construction was secure under an abstract dual key cipher scheme. Moving on, we proved the dual key cipher scheme construction secure under abstract PRF. Then regarding the oblivious transfer protocol, we proved its security under the decision diffie element assumption and under an abstract entropy smoothing hash function. And then having these two concrete definitions, we were able to define and to derive the security for the instantiated protocol. We also did some compositional reasoning in the crypto sense. We did some hybrid reasoning over distributions, and we did some hybrid reasoning over wires in the circuit, which was actually the kind of reasoning that allowed us to finish the proof of security for the garbling scheme. So one interesting aspect of our proof is that it was carried on over an inefficient specification of the protocol that was not suitable for program extraction. Therefore, we specified another version, more efficient, of the Ers Efi protocol, and we proved these two versions equivalent. So, as I already said, our verified implementation was then obtained via the EasyCrypt extraction mechanism, and we instantiated the abstract leftovers using CryptoKit and just Garble. So I have here some time measurements of our verified implementation. As you can see here in this column, the total time the verification overhead starts to notice. So now let's see how these two components can work together. To combine them, we decided to use the Fresco framework, which, as already said, is a framework for secure computation based in Java. And we use Fresco to deal for communications and for circuit parsing for us. So, having a C program, one can use the CircGen compiler to certifiably obtain a Boolean circuit, which can then be fed into Fresco, that inside of it has this Varial protocol suite that is able to call our verified secure computation engine that can securely evaluate the Boolean circuit that was previously generated. So here are some measurements that we collected in Fresco. We did two kinds of comparisons. We compared both the execution times of circuits generated with CBMC and with CircGen, and we also compared the execution times between our verified implementation of YAO and the tiny tables implementation that came with the vanilla distribution of Fresco. So as you can see here in this table, the execution times are quite different, but note that the preprocessing and short optimizations are actually visible in this tiny tables implementation. So to conclude, our main focus and the main focus of this work was actually in the verification process, both in terms of programming languages, as we did certified compilations from C to Boolean circuits, and also in terms of crypto, as we did the verification of an interesting proof of security. I'd like to finish with some final remarks. It is actually possible to have a verified stack of this kind, but it comes up with a great effort in program verification. We did some interesting combination of PL in crypto tools and techniques to come up with these stacks, and this is what we think we actually came up with viable end results in terms of efficiency, meaning that it's actually possible not to lose that much performance if one apply formal verification techniques to the development of these kinds of tools. So I finish up showing you the access to our development, and I'm open to questions.
So Brian Parno from Carnegie Mellon. So this is a nice existence proof that shows that this can be done, but are there general lessons we can learn from this for future efforts?
If there are general lessons that we learn?
Yeah. So
well, the main lesson that we learn is that it takes a lot of work.
Any ideas on how to make it take less work the next time?
Less work. Well, we could achieve better integration between all these tools. When we were working with CompCert and Cockwin on one hand, EasyCrypt in other hand, and then we have a Fresco framework on the other hand, and it's kind of hard to integrate all these components. So if we achieve better integration with certified compilations, proof techniques, and prototyping tools, actually that would turn the process a lot more easier.
Thanks.
We are not thinking about that. Of course, it's some kind of possible future work, but yeah, that would require even more effort in terms of program verification. Actually, as this even here we are targeting only passive security. So even if we move on to malicious security, that would represent also a great amount of effort.
Hi, co-work, Vince from Alibaba. I know there are other compilers which make functions into circuits. For example, the EMP by Xiao Wang. So, what is your difference between your generated circuit and compared to theirs? Yours are 100%, while theirs are 99%. Is it like that?
Can you repeat, please?
What is your the difference between the circuit generated by you and generated by other compiler?
Well, our compiler is certified, so you have the assurance that the Boolean circuit that you come up with actually gives respect to the C program that you started the compilation process with, and I think that that's a plus.
Will it be bigger or smaller than the circuit generated by other compiler?
Depends. As I show you on the gate counts for CircGen, we had some classes in which our compiler works better. Even the non optimized version. But if you use the optimized version, which is still not yet totally verified, you can achieve the same kind of circuit performance that other tools that are actually non-verified.
Okay, is the circuit generated by you usable by other framework?
Yes, yeah, you can use it in other. Every framework that reads Boolean circuits in Bristol format can use our CircGen compiler.
Great, thank you.